I've also put the slides out on the Discord so people can look back later or skip ahead if they're fine with going a bit too slow for them. But yeah, so this workshop is going to be based around performance and practice. So the first one was kind of just intro to like C++ syntax, because that's very helpful for competitive programming. Then most of the workshops for the remainder of the year are going to be based around algorithms and data structures, which will help you solve various different problems. They come up all the time, they come up in industry, they're very helpful. But this is kind of like the intro to that, because before you can actually use them, you kind of need to know whether an algorithm or data structure will work to solve a particular problem. And so there are properties of them that we'll go into later, but the main thing is actually, is it fast enough, which is something that will come up a lot. And so that's where we're going to kind of start with some areas that you might see when submitting your code on AUCPL. So there's a bunch of statuses here. Two of the big ones are these two, time limit exceeded and memory limit exceeded. And so this is an example of, this is memory limit exceeded. It's really a runtime error, that's what the RTE means, but it's because memory ran out, which is what the bad allocation is. And time limit exceeded would look something like this, where you get this TLE. And so that TLE is probably the most annoying thing you'll come across when you're trying to do competitive programming questions, where you've got a solution, it's working, you've tested it on your device, you go to submit it, it passes all the test cases, but then there's one or two at the end where it TLEs because it's not fast enough. And so the reason for that is generally your algorithm is just too slow. When the people wrote the question, they had an idea in mind which runs faster than what you coded up, and the faster solution is what's needed to successfully pass that problem. So how do we go about fixing these errors? For memory limit exceeded, use less memory, and same for time limit exceeded. So that's good advice, but I feel like it's probably go a bit more specific, but that is the gist of it. So we're going to start by taking a bit of a detour to go to sorting, and then I'll relate this back to how you can see how fast your code is and take up less time afterwards. So this is some examples of sorting in C++. So we briefly went through, there was like one question I think last time that I got you to try sorting with. This is kind of a more advanced one, because I think there are some questions that you might find sorting helpful with in the competition on Saturday. And so just to run through this code quickly as an example. First I've got two different arrays. The first one's just like a standard vector. Next one is a bit more complicated. So this is like a nested data structure where I've got this vector, which is like an array, if you remember that. And then this array is a fixed size one. So in C++, a vector is like a variable length list or array, and array is fixed length. So this specifically one is an array that contains integers and has 3 of them. So it has exactly 3 integers and no more, no less. And so what this ends up being is a vector of 3 length arrays. And so you've got a list of however many sets of 3 integers, essentially. So that's what we've got here. I've initialized it to these values. So I've got 3 different sets of 3 length arrays in that vector. I'm just using these 2 vectors for various sorting examples. So first this is the one that we saw on cplus.com, or C++ reference, if you had a look at that in the first workshop, where you can use this sort function that just sorts by default in increasing order. So this would sort that 1, 3, 4, 6, 9. If you want to, so that's great and all, but often you'll want to sort something by other criteria, because always in increasing order, it's great if that's what you want, but it's not necessarily what you're looking for. So the next most common thing is probably decreasing order. And so C++ has got an inbuilt function for that. So you can also pass a third parameter here, and that's called like your comparator, and it specifies how you want to compare the elements while sorting them. And so this one is basically just a built-in function that says we want to use the greater function. If you're comparing 2 integers, if the first one is greater than the second one, we want it to come first. And that's really what this function is. It's just any function that returns some Boolean value of whether they're in the correct order or not, or whether they need to be switched so that they're in the correct order, whatever you define that correct sorted order being. So this third line here, that does the exact same one as line 9 there. It sorts it in descending order, but I just made this more explicit. So assuming that maybe we didn't have this built-in function or you didn't know about it, this is a way you could do it. So this syntax is a bit scary, and so keep in mind that you can bring in as many printed or handwritten notes as you like into the contest. So I'd suggest like writing down some of the syntax if you think you might find it helpful. But this is what's called a lambda function. It's basically just a one-off function that you're using here and nowhere else. So you don't bother defining a whole other function with all the syntax. You can just use this shorthand. And so what this is basically saying is this square brackets is if you want to use any other variables that you defined, like array or array2 up here. In this case, we don't need any other external variables, so we just leave it empty. Then you've got your like circular parentheses, which is your like input to a function as normal. So in this case, a comparator always takes in 2 elements, the 2 elements you want to compare. I specify the types to be auto references because I don't care what types there are. I know there's going to be exactly 2 of them, so I'm just not bothering with that really. I just call them left-hand side and right-hand side. And so then this function should return true if these are in the correct order. So if left-hand side should become before right-hand side in sorted order. And it returns false if they should be switched around. So in this case, if we want descending order, if the left-hand side should come before the right-hand side, it means it should be greater than it. So we're just returning, is it greater than that right-hand side? Are there any questions about that so far, or anything confusing? Cool. So yeah, then I just printed it out. So that's this example here. It just sorts to that first array in descending order. Then here's a more complicated example with more complicated data type. So this kind of 2D nested array. In this case, I still got the same structure here, but the comparator I'm doing is comparing the second element. So remembering that indexing starts at 0, it's comparing that second element in that array of 3. And again, doing greater than. So it's going to sort it in descending order by that second element specifically. And so I printed it out here, and you can see that it's using this array2 that I passed in. And this second element, so 962, is going in descending order. And that's what it's using as the sorting criteria. So then you can kind of do this with any data structure you want. It just depends whatever you define up here. And you can have whatever you want really in this sorting function. And so you can define whatever order. Does anyone have any questions about that so far? Yes, Jason?
Just for the auto address here, I thought you could just do like auto and that would be for all data types. Do you have to specify address?
You can do auto. So auto would work the exact same way without having this ampersand, which means the reference, if you remember that from last workshop. The reason I have that reference is because we're going to get to this as this relates to the speed aspect of it, where if you don't have the reference, it's actually going to create the copy of the objects you pass in. So in this case, when I'm passing in like arrays, if they were big arrays, it would have to copy all those values, which could lead to your solution being too slow if you're trying to submit it to a problem. With this, it's just basically doing a pointer. Have you guys started C yet in MATLAB and C? Yeah, so it's basically just passing a pointer, which is effectively a constant like amount of time. It's not going to make a difference. And so auto-reference, because it has the same functionality, having that ampersand is always going to be faster, so you may as well do it pretty much. Yeah, any other questions? Cool, so I've got an example to try out now. If you go to this page on AUCPL.com, it's going to have a similar question where it wants you to sort something in a particular order, and you'll need to have a go at using that custom comparator. So, have you got it? Yeah. Yeah, so have a go at that. Once everyone's typed in the URL, I'll go back to the other page so you can look at the notes or the example I had there. Everyone happy for me to continue on now? Yep, all right, cool. If everyone can quiet down a bit. Yeah, Nick, I'm looking at you. Okay, so I think most people managed to get it, or at least get the right idea. And so the solution here, ignore this. I did this on my Mac, so that's not working. But basically, the general idea was we do the same thing with we have a custom sorting function. And if the last digit, which we get by doing the remainder mod 10, if they're not equal, then we just compare by that last digit. If they are equal, then we compare by just the number in general. Yep. Okay, so next we've got 2 questions for searching. Ignore the second one for now, just have a go at the first one. It's about finding whether basically an element exists in an array and where it is. It doesn't require anything special right now, so you should be able to have a go at some of the solution by yourself. And then we'll walk through that after. Yeah. So we're going to take a break from that just for now. You can keep thinking, if you haven't done it, I think some people have gotten it, but if you haven't yet, keep thinking about it in the background. I'm going to skip past the answers for now, so don't read that. Just because I don't want this going for too long, so we'll head back to that at the end. So onto what this was originally about, measuring performance. So there's a reason why I did all that stuff first. So we did sorting first, which is in general helpful, but you might have noticed the second question or / pair of questions provided you numbers in sorted order. And the reason for that is there are different ways you can solve that problem that will be one significantly faster than the other. But the key thing is, how do we actually tell beforehand? Because you don't want to code something up, test it, it doesn't work, and that's how you find out that it's not fast enough. You want to know beforehand so you don't have to waste all that time on something that isn't going to end up working. And so the way we measure performance and figure that out in computer science is something called big O notation, which you might have heard of. You'll learn much more about it in second year usually. But it basically tells you how fast something scales with the input. So I said it gives the order of how memory or time grows with the input. Usually time is the big deal, memory is not a very important factor. So it'll generally be referred to as time complexity, you might have heard. But basically, there's a few mathematical rules about it. We won't go too in depth because you don't really need to know all the maths behind it, just how to apply it in general scenarios. So in general, if this is the number of operations you have, so maybe you've got an algorithm with 5 operations or 3 n operations where n is the size of that input vector, so the number of items you need to sort or you need to search through. We can just drop these constants. We only care about how it scales with the input. So if it's always 5 operations, it doesn't scale with the input at all, so we just say it's constant. If it's 3n, then it scales linearly with the input. If we double the size of the input, it's going to double the amount of time it takes to run. And so that's an example of a linear time complexity, quadratic, etc. So in general, we just don't care about these constants because they don't tell us about how it scales with the input. We don't care about a specific value, just how it grows. This also means it's the largest term that dominates. So here's a few cases where we've got the 3n plus 2, because we drop all constants, and then because linear is bigger than constant, it just ends up being overall linear, because that constant term isn't going to make a difference with how it grows in the long term. Same here, where we've got a bunch of different polynomial terms. The cube term, which is the largest, is the only one that's going to dominate how it grows with that input size, because the other effects are going to be negligible pretty much compared to this n cubed term. And another example, so factorial, you guys should all know that factorials grow massively. Once you get to 10 factorial, it's some almost like a billion, I think, and then it grows stupidly from there. And so the factorial term easily dominates the n log n term. So then we've also got, this is more advanced, this won't come up as much, but so in this case I've just said everything in terms of n, where n is probably usually something like the size of an input list. So in this case, either sorting or searching, you're given a list of numbers. You can have multiple different inputs, so in this case I've used x and y, and you can't necessarily drop everything like I did in the previous example, because you don't know how x and y are, how big they are compared to each other. If we know x is way bigger than, so actually first here I've just dropped the constants and done any this x is bigger than log x, so I've done those simplifications already with these two. So you can't simplify this anymore without more information, but if you know x is way bigger than y, then this becomes x plus log x, and so the x term dominates. If you know y is approximately equal to x squared, so I've used that big O there as well to say it's about the order of, then if you sub that in there, you get x squared plus log, or x plus log x squared. You can use your log laws to simplify, it still comes out to O of x. If you know it's this size, which is this is huge by the way, x to the power of x, you won't see that in most code. That's going to take a really long time to run. But then again, using log laws to simplify, this x log x term comes out to be bigger, and that dominates the whole thing. In general, this isn't as important. The main thing is just being able to do it with one single number, which is usually the size of an input vector. Although it is important often to think about what this n represents, because it will change in the context of the problem. So here's a hierarchy of common growth rates you'll see in actual programming problems. These are all the ones I think I've basically ever seen, and most of these are still pretty rare. The ones I put in red are the only ones you'll see on a really common basis. And so these ones are factorial, which comes up often in mathematical problems when you're doing permutations, if you remember that from high school maths. Exponential, which is usually when you're picking between 2 different options at every step. Quadratic, which is something like doing a double for loop through an array. N log n, which will come up in sorting, you'll see. Linear, when you're doing something for each element in an array. Logarithmic, when you can halve the search space each time. And then constant for any maths operations usually. Okay, so I've got some examples for each of those common ones, just so you can see what that would look like in actual code. So for constant here, I've just done a bunch of random maths. I don't know what it does. I do have a for loop here. You can see the for loop is doing exactly 50 loops each time, so it doesn't matter how big this x and y is, because this doesn't change with the inputs. That's why it's still constant. I don't care what's going on here. All I know is that I can make x and y as large as I want, and this will still run in about the same amount of time. Next, I've got an example of log n. And so this is, again, I'm taking in a number, and then I'm iterating through it, but instead of iterating through like each number from 0 up to it, I'm doubling it each time. I've just realized there's actually a mistake here. This should start at 1, because otherwise I'm doubling it, it'll stay at 0 each time. So ignore that, but pretend this starts at 1. But if you start at 1 and doubling it each time until you reach n, there's only so many times you can double it until you get up to n, and because you're growing like at a faster and faster rate, this will end up taking log n operations. If you kind of think about doing like the equation to solve for that, how many times can you double something? Well, 2 to the power of x equals n. If you solve for x, it'll be log n, log 2n specifically. The base doesn't actually matter. They all end up being about the same, so we just care about the log part. Linear, doing something for each element of an array, or in this case, for each number from up to this input. So if we double n, this for loop will have double the amount of iterations. We got n log n. So in general, another rule is if you're doing something inside of like a loop, you multiply the time complexities. So here I've created this. This is the one that we had an example for before with the logarithmic time complexity, where it's like doubling at each step. Again, pretend this starts at 1. So I've just got that here, this function, so this line 18 is going to take log n time to run, or really it should be log I, because that's the input that we're passing in here. Then I've got a for loop that runs n times. So in general, when you've got something nested inside a for loop, you multiply the time complexities together. So this loop will run n times. Inside, the work done in each loop is going to be log n. So we multiply them and we get n log n. You might have noticed that because this is I, this will start at being 1, then 2. So it won't actually do n things for each iteration. But in general, we just kind of round up. So in the worst case, this is going to do log n work in each iteration. And so overall, it'll be n log n. Does that make sense so far? This is more of a tricky example, but does anyone have any questions about that? Cool. N squared, so nested for loop like I mentioned. This is a common one again, where we're just going n iterations of the outer loop, and for each of those iterations, we have up to n iterations of the inside loop. And so we multiply them together, we get n by n is n squared. 2 to the n, so like I mentioned, that's usually doubling your amount of operations at each step. So I've got calculating the Fibonacci number. I assume everyone's familiar with the Fibonacci sequence where you add the previous 2 numbers. And so I've got a recursive function here, the base case, and then you're adding the 2 previous numbers, just using a recursive call here. And so when you're finding the nth one, because when you go down to finding the previous one, it's going to do 2 calls, and then for each of those, it's going to do another 2. It's going to like double each time, and that's why you get this exponential 2 to the n. There are a lot of ways actually you can speed this up. I won't go through them now, but you might be good to think about those. And then n factorial. So like I mentioned, that's often to do with permutations. If you've got like an array of length 10, there are 10 factorial different ways of arranging each of those numbers. This is a bit confusing to look at if you haven't seen it before, but next permutation basically takes an array and gives you in either increasing or alphabetical order the next permutation, so the next arrangement of those numbers. And so basically making a copy of it and then going through every permutation until you get back to the start, what this while loop is doing. And because you're going through n factorial different permutations, you're going to have n factorial work. With kind of one catch, does anyone see why it might not be actually n factorial here? It's to do with what I mentioned on some previous slides about nested loops. So this is n factorial, but there's looking at first glance it might not be for a reason to do with nested for loops. So it's something to do with this while loop. Do you have any idea why this might so this will definitely do this while loop will run n factorial times. Is there any reason why the whole section of code might not be n factorial? Do any of you guys know? This is a tough question. I'm not expecting anyone to get it, by the way. I just thought I'd ask.
I guess if you have 1, 1, 1, 1, 1, 1, then surely that would
Assuming they're all unique, but
okay.
Yeah, that would break it a bit. But if we assume they're all unique, there's still a reason why it might not be at first glance. It's to do with this line here, 17.
If the next permutation is the one that it's looking for?
Kind of. So yeah, that would end it immediately, but in general, we're looking at the entire lifetime of the program, and so as it starts at this one, it won't get back to it until it loops back at the end. But you're definitely on the right track there. I can see all the second years and Nick are confused as well. So don't worry that none of you guys are. I think you're closer than these guys are. But the reason is, so I mentioned before, if you've got nested loops, you usually multiply the time complexities. And so this while loop will run n factorial times, assuming all of the numbers are unique in the array. But that's only going to be n factorial overall if this next permutation function runs in constant time. And so if you initially think about it, it might seem, how can you find the next permutation in constant time? You'd have to reshuffle the whole array, which would usually be O of n if you're doing something for every element in an array. But if you go to cppreference.com, if you look at the implementation, it does say it might be up to O of n, but on average, it would take I think 3 swaps, which is constant over the course of every single calling of it.
What do you mean constant time?
Constant time, yeah. So on average, so I'll explain this a bit better. So it says O of n in the worst case. So it could do for however long this array is, it might take an order of that many operations to call the next permutation function once. But on average, so especially since we're going through every single permutation here, we're going to hit that average. It only takes 4 swaps. I think it's 3 or 4. And because 3 or 4 swaps it doesn't change with how big the array is. It's still just doing 3 or 4 swaps. That's why it's constant. Does that make sense?
Sure.
Yeah. So it might do up to say n swaps on a really bad case, but since we're going through every single permutation, on average it's just going to be 3 or 4. Does that make sense?
I have a question.
Yes?
Is next permutation a built-in function?
It is a built-in function.
That's crazy.
Yeah.
That's crazy.
This is it makes it really easy to do some really annoying combination questions that you
No. Well, there is.
This is why you learn C++.
There's a combination library.
Do you guys remember how to do this stuff? I changed it and I lost it.
Okay, so continuing on, sorting revisited. So this was the answer to the sorting question before. Can anyone tell me what the time complexity of this would be? Not anyone who's passed their year. Yes. How do you know that?
I learned it at some point.
Exactly. Yeah. So you can't really tell by looking at this code that it's n log n. You just need to know that sorting is basically n log n in the average case. If you didn't actually know where to start with this, the way you'd figure that out is if you look here. So obviously taking the input's going to be O of n, printing it out's O of n. All this stuff in here is just constant stuff. So it's just this sort function, which is some magical function that sorts it for us. So you just go to cppreference.com, find the sort function, and it tells you somewhere that it's n log n. So in general, that's what a lot of this will be. I might actually see if I can see here. I think. Oh no.
But you guys both on time?
Oh, there we go. Great. If we go to cppreference.com.
Can you see that wizard code? Should we
Saw it.
if you read this code, when you look at it, you should have some compiled issues.
Yep. Okay. So whenever you're looking for some built-in function on cppreference.com, there's this bit here that's complexity. Guys, can you quiet down? And so n given as last takes first, so that's just how many elements you're sorting essentially. So in an array of n, that's what n is, the size n, and does n log n comparisons. So because we're using a custom comparator, but it does constant time in each comparison, it just does n log n comparisons. So we'll be O of n log n. All right, it's getting a bit late, so we're going to move on from here, just so we're not around here for ages. But yeah, so I think a decent number of people managed to get a solution for that working. And so this is what I had for a basic solution, where I'm reading in the input. Actually, no, this is a set run. So I've defined my input here. I didn't bother reading it in for the problem. So I've got this search function, which basically loops through every element in this array from index 0 up to the final index. If it's equal, it returns the index, otherwise it returns -1, and I'm just printing it out here. And so the reason we went through all of that stuff about big O notation is because there is a better solution than this. So can anyone tell me what the time complexity of this search function would be?
N?
Yeah, so we're doing something once for each element in the array, so it'll be O of n. And so it's good. O of n is pretty good on average, but we can do better, specifically because the input was in sorted order. And so I think I definitely heard some people talking about it, but the way we can do this is with a binary search, if you've heard of that. So basically, here I've just got 2 search functions with different parameters. Don't worry about that too much. It just means if I call it with 4, or if I call it with 2, it'll call this one. If I call it with 4, which I'm doing here, we'll go to this one, just so I can start L and R at 0 and the end of the array. So these are just indices marking the left and right hand sides of the array that I'm currently looking at, which starts at the entire array. And then while these two are like separate, so while they're more than one apart, essentially, I'm finding the midpoint of that. If we found the thing we're looking for, then we can just return that. If it's too big, or in this case, if it's too big, then we move that right-hand side of that we're looking at to the middle of the array, because we know it must be to the left since it's in sorted order. Vice versa. If it's too small, we move to, or if it's too small, we move so we're looking at bigger numbers, and then repeat that until either this is no longer true because it's just not there, or until we find it. And so to kind of like visually display that, so with this one, we're basically going through one at a time, is this number equal to what we're looking for? And so you can see we have to like check the entire array. With this one, we're starting looking L and R at both ends. We check the middle, so say we're looking for 6. Is 6 smaller than 13? Yes, so now we're looking between 2 and 9. So we go to the middle, we found 6, we can return. So that's 2 checks instead of like, oh, how many are there, like 8 or something. So you can see why that's going to be a lot faster on average. Does anyone know what the time complexity of this function would be?
Less than the other one.
Less than the other one? Yep. Do you know?
N maybe?
Sorry?
1 over n.
Not quite 1 over n.
Log n.
Log n? Yeah. So log n. So I mentioned before, log usually, guys, can you quiet down a bit? So I mentioned before, log usually comes up if you're like halving the search space each time. So in this case, because we're cutting this in half each time and eliminating either one side or the other side, we're cutting like in half each time. We can only do that so many times. And if you like think about the equation for that, it's basically, if we go about in reverse, you'd be doubling it. So that's 2 to the power of n, or 2 to the power of x equals n. If you like solve that equation, you get x equals log n, which is the number of times you can half the array before you run out of elements, basically. And does that make sense to everyone? Yeah, cool. And so yeah, this means that this one will run a lot faster, especially for large inputs compared to this one. Okay, I'll get back to the end. And so the key thing here with this one, so it is faster, but the main drawback is that we did need it to be in sorted order, otherwise it just won't work. And so it would be nice if we could always have elements sorted, so we can always do this, in certain scenarios at least. And so we won't go through this in detail today, but that's what binary trees often used for. So basically, instead of keeping a list of numbers in just a list, we can keep them in this tree structure where every number smaller goes to the left and every number larger goes to the right. And so you can do that same kind of pattern where you're splitting it in half each time. If we're looking for, say, the number 6, 6 is larger than 3, 6 is larger than 5, and less than 7, and then we find it. Or if there's something that doesn't exist that we're looking for, say like 4 is not here, we can go 4 is larger than 3, smaller than 5, there's nothing here, so it's not in the tree. And so we'll go into a bit more of this in the next workshop. This is kind of just so you know it exists for now. But yeah, it's a nice way of keeping track of any numbers that you might want to search for in a particular order. And so if you want to say insert, I think 4 is the example I used. Yep. So then you do the same thing, but when you find an empty space, that's where you insert your number. So yeah, this basically converts a lot of problems that would take O of n time usually into log n, because you've always got that option of splitting it in half each time when you're either inserting a new number or looking for a specific number. There are some catches there, but we'll go into them in the future. So practice quiz, we won't go through this right now, but I put up a quiz there's a GitHub page which has got a bunch of code samples that you can use to just test to see if you've got a good idea of being able to understand what the time complexity of a given section of code is. There is one error in it. If anyone has a go at this later and wants to know what the error was, feel free to message on the Discord and I'll answer. And then, is it fast enough? So it's great that we know this like theoretical big O stuff, but it doesn't help us with actual AUCPL. How do you know ahead of time, is the code going to work? In general, 10 to the 9 operations is the limit for the upper bound of things you can do before you're going to run out of time. And so what you can basically do is, this is a general rule of thumb. You can write these down on notes you bring in, or what's easier is once you come up with your big O, you can basically just plug in your n, whatever it is in the worst case. So on all the AUCPL problems, you should see, it'll say like the input will range from this to this number. If you just look at what's the largest it can be, replace it, substitute it in for n here, put that in your calculator. If it's bigger than 10 to the 9, it's probably too slow. If it's about 10 to the 9, you might be okay, but it's on the edge. And if it's less than like 10 to the 8, then you're safe. And so that's an easy way, once you come up with an idea and you know its big O complexity, is it going to work before you even have to code it up? So that can save a lot of time on working out whether your solution is fast enough to a problem before you actually try and submit it. So that's mainly for time. Again, I also mentioned memory at the start. Memory is a lot simpler. Usually it's never an issue. In general, you can have an array with about 10 to the 6 elements in it. Bigger than that, it's not going to work. But yeah, that's really an issue. So just keep that in mind. Sometimes if you're like trying to take in a really big array, that might be why you're getting an issue, but I haven't seen it very often. This I basically stole from this Code Forces page. So have a look there if you're interested. It basically says the same stuff. I made a few modifications that I prefer, that I think are a bit more accurate here. But yeah, it's quite useful and goes into a lot more detail in the comments, I think, as well. So then 2 more slides. So resources. So we haven't had time to go through too much today, but if you want to do more practice on your own, which I'd highly recommend if you want to become like really good at this stuff, there's 5 main things I put here. The first is the Algorithm Design Manual, or the ADM. If you guys have heard of RSP, that's like one of the requirements at the start of the program. You have to read through it. It is very like theoretical and quite verbose, so it is quite challenging to read initially, especially when you're not too familiar with programming or algorithms or data structures yet. I'd recommend it if you feel like it, but if you get discouraged, don't like feel like you have to like read through this thing immediately before doing anything else. You can do it bit by bit. You can take other approaches, but it is quite a good book just for the theoretical aspects of it if you want to know more about that. For more practical stuff, these 4 websites are probably the best ones. So Code Forces has a bunch of like competitive programming problems and contests and also past contests. So that's probably the best practice you get for specific competitive programming stuff. USACO is kind of the United States like competitive programming organization. They have a bunch of guides. They host competitions as well, but they have a bunch of guides, especially this USACO guide, which basically takes you from the very beginning of programming up to like elite level competitive programming techniques. And so there's a lot of really good stuff on there. They've also got, so it's mostly like written like walkthroughs, but they've also got, I think, a full like YouTube course on like bronze level, which is kind of beginners up to like intermediate level. And so that's really useful if you want to have a look at that. ICPC and SPCPA, so that's the International Collegiate Programming Competition and the South Pacific Competitive Programming Association. So ICPC is like the main international competitive programming competition at university level. SPCPA is Australia's main like body for competitive programming. And so they have a bunch of past contests, a bunch of resources. This is the SPCPA, the Australian one. They've got a bunch of training resources, which includes like a bunch of recommended guides as well as I think a live, so like we have an AUCPL, you can do the problems any time. They've got a similar thing for all of the past, I think, ICPC contests, which is like the world standard at university level if you want to have a go at seeing what those questions are like. And then LeetCode, I'm sure most of you have heard of that. LeetCode is less, it's not really the same style as a lot of competitive programming questions, but it's still the same data structure and algorithms stuff, and it's good for getting those basics down, and especially because they often have good either LeetCode provided solutions or a lot of community provided ones. So it's really good to like get that fundamental practice in. And so I'd recommend doing plenty of those, and especially when you're learning specific topics, you can go search by those topics and just practice questions there, which is really helpful. I had like 4 questions I'd recommend doing now, kind of related to this stuff / what might be on Saturday in DIV B. We won't do that now because it's pretty late, but the slides are all in Discord if you want to have a go at these questions or any others you feel like. So yeah, that's everything. Feel free to stick around for a bit if you want any help with coding up the searching questions still. But yeah, let me know if you've got any questions.